Okay, so we're starting Module 3 today, and this is on physical organic chemistry. You'll notice I deleted out the chapters. Those are from the old book, so I'll have to update that. And in Canvas, I'll link it to your new textbook. Your exam 2B is graded in zip grade, so you can see your score on that. So at this point, we've learned about how to apply the Lewis dot structures to make functional groups, to make molecules. We've learned the spectroscopic methods to figure out what the structures are. And now in this module, we're setting the stage for really the rational determination of where a reaction is going to take place. The important part of this is acidity. And so we're going to review a little bit of general chemistry, where in that class you learned primarily about strong acids. So there are strong acids and weak acids. Strong acids primarily ionize completely. So those are sort of straightforward to understand. But for this class, in organic chemistry, we're dealing with weak acids. Those do not ionize completely. So we calibrate strong and weak acids on the pKa scale, and then we're going to associate a number with the functional groups that you've learned. So we'll see an example today of a molecule. We'll list out the functional groups, and then we'll talk about acidity. So the point of this is we want to rationally predict where on a molecule a reaction is going to take place. So the exercise of determining the unique sets of hydrogens is directly related to this. As we move into modules 4 and 5, when we start learning about more reactions, a question you might have is, how do I know where a reaction is going to take place? So the concepts in this module will give us that understanding. Any questions before we dive into it? So at this point in the semester, as I said, you should be familiar with a couple things as we move forward so that you're not feeling left behind in the new concepts we're undertaking here. So, given a structure, how do you figure out the molecular formula? How does mass spectra, how does that piece of analytical data tell you about heteroatoms present? How do you calculate degrees of unsaturation? What functional groups are present? So IR is good for that. How many unique carbons are there? We learned how to classify the attached number of hydrogens by calling them methyl, methylene, methine, and quaternary carbons. Where would you expect to see those carbons on the carbon NMR based on hybridization and functional group? How many unique sets of hydrogens are there? Where do you expect to see those on the proton NMR? And then what is the way the signal looks like? What is that telling you about the number of neighbors, so the n+1 rule? So new to this module are, based on the functional groups present, what's the most acidic hydrogen? So that's the question we have to figure out, and that's the guiding principle of where a reaction is going to take place. So in terms of an exam, how could you think about this? Given any set of hydrogens, rank them according to acidity. And the rational way you do that is according to the pKa scale, which is a number. Associated with that is, what is the strength of the base that you need to use to abstract a hydrogen? So the most familiar base that you've encountered in chemistry is probably sodium hydroxide. So you can use that for some functional groups, but not all of them. And again, we're talking about matching pKa numbers at this point. What we'll also get into as well is this concept of stereochemistry a little bit later on in the module. So that deals with a new type of isomer where you have one formula, you have the same connectivity of all the atoms, but the spatial arrangement is then different. And then we saw a little bit last time about the Newman projection. That's going to be important for us in helping predict the outcome of a reaction. How does the conformation, how do sigma bonds rotate to allow a molecule to get into a reactive conformation? So let's all calibrate ourselves on a review of some general chemistry here, acidity. So from your recollections of acids and bases, is sulfuric acid, H2SO4, a strong or a weak acid? So sulfuric acid is a strong acid. So I'm going to use these terms strong and weak as to just sort of put the acids in two different buckets. But amongst those buckets then, there's levels of acidity. So I would think that this is the new concept for you all, and really the minutia is when we get to the weak acids, because we have to match them with base strength. So H2SO4, what about acetic acid? CH3CO2H. That's a weak acid. How do we know it's weak? So acetic acid is the taste component in vinegar, which is in Italian dressing. So if you go to like Olive Garden, you get the dressing, that pungent sort of astringent taste is acetic acid. So you can eat that. Can you eat sulfuric acid on your salad? Probably not if you want to live long. So there's just a difference, right? So which acid is stronger? Therefore, it's sulfuric acid. So those are just qualitative descriptors of those two compounds. So I put, what you'll notice on the slide here is I put water up there. I drew that in for reference. So if the acid moiety, that just means component of sulfuric acid and acetic acid, is the OH group. So let me highlight that. So I'll highlight that in green. And then I'm going to highlight it in water. So the OH group, that H is the acidic proton. If that's the acidic proton, why are we using these different qualifiers? Why are we saying one is strong and one is weak? And really what we want to figure out, I'll highlight in yellow. See the rest of the molecule here? How does the rest of that molecule influence the OH bond? And so we're going to talk about factors that influence acidity. And, on this slide, I'm just showing OH. But the majority of the functional groups that we've learned so far this semester are CH. So that's probably the new thing for this class. We have to start thinking of acidity in terms of CH bonds, because that's what a lot of organic molecules have. So when we consider acetic acid, how many unique sets of hydrogen does it have? So there's two. You have this H, and then you have that CH3. So there's two unique sets. And we already saw that the OH is acidic. But the CH is also acidic. So you have a molecule that has two acidic functional groups. So the ratio of that was 3 to 1. Now the question is, if you treat that compound with a base, what gets deprotonated first, the OH or the CH? So the OH is going to be deprotonated first. And so why is that? And that gets to the question of what we're trying to figure out in this class is where exactly is a reaction going to take place? And we really want to demystify when you get to this issue of, okay, there's two paths I can take, which path is the right one? We want to do that in a rational way. You don't just want to be like throwing spaghetti at the wall and hoping you get the right answer. So if we were to take acetic acid and we treat it with a base, sodium hydroxide, the products of that would be that anion. The negative charge is then balanced off by the sodium cation. And then the other product would just be water. So acid-base reactions talk about proton transfer. So the action of the base is to abstract a hydrogen or a proton from the acid. And then from general chemistry, we learned about for every acid base, you have a conjugate acid-base pair. And that then leads into the nature of this arrow right here. For a strong acid, you're predicting which side of the reaction the equilibrium will lie. So we're going to talk about equilibrium, those expressions, and then how it relates to this thing called pKa scale. And that's the scale in which we actually put numbers in. Then from the numbers, we can rationally predict what happens first. So when we look at that, sodium hydroxide can definitely deprotonate the OH. The CH3, probably not. So why is that? So the difference in the OH versus the CH acidity is pretty big. And then that base is not strong enough to deprotonate a CH bond. So we're going to look at OH, CH, then all the rest of the stuff near it and how that affects the acidity value. So to check in, we'll do the molecule gifratoxin. I'll walk you through what the issue is. The apixaban one you can sort of do on your own as a check-in. So what I'll do is I'll name some functional groups. We'll talk about hybridization, and then we'll see what this issue is with where a reaction is going to take place. So up here, I'm going to draw this H in. So this is a terminal alkyne. So of the alkyne, we know that that carbon is sp hybridized. So moving along the chain, we have a cis alkene. So cis means same. Those two substituents coming off are on the same side of the double bond. So we have these H's here. And we know those carbons are sp2 hybridized. I'm going to switch the pen over to blue here because we're going to march along the backbone. And we get to here, we see that that carbon has two H's. And so it's sp3 hybridized. In the way that I'm going to classify it, it's an alkane. Just in general, it's a saturated carbon that's sp3 hybridized, the CH bond, so I'm going to say alkane. And then we go around, and I'm just going to highlight in blue all the sp3 hybridized carbons. So we get to the end, and then we have a primary alcohol. So we have all these functional groups. You can determine the total unique sets of H in there. There's quite a bit. So the question is, if you treat that molecule with a base, what functional group gets deprotonated first? You have a lot of CHs. So you have sp carbon H in the alkyne, sp2 carbon H in the alkene, then a whole lot of sp3 carbon H's in the alkanes, and then the OH. So if we were to grab a base, throw it in there with the gifrotoxin, what's going to get deprotonated? So it turns out, regardless of what base you choose, the OH will get deprotonated first. And so the reason I know that is based on the scale that we'll learn. That's the most acidic hydrogen. But then the follow-up question to that is if you were treating with a second equivalent, by equivalent I mean ratio. So we fully deprotonated the OH, we put in another equivalent of base, what gets deprotonated next? So that is what's going to guide us in terms of reactivity. And then you can do sort of the same analysis for apixaban, just to refresh your memory on functional groups, hybridization, and those concepts. So I've listed some of them for you there, but it's still helpful to understand what the names are, review the hybridization, classify them, methyl, methylene, methine, or quaternary. Think about where they would occur in the carbon NMR, the proton NMR. All of that stuff is, we're still going to rely on that moving forward. Questions so far? So to set the stage for acidity, we're going to review the strong acids that you learned in Gen Chem, and towards the end of this class today, we'll get into the weak acids, which are all of the functional groups we learned from Module 1. So to really calibrate acidity, we're going to talk about water. So we all know water is H2O. It's the universal solvent on Earth. So we refer to water as aqueous. So it's a polar protic solvent. All the organic molecules that we've learned, those are organic solvents. So those are typically non-polar. So the molecular weight is 18 grams per mole. Its physical properties, it freezes and melts at 0 degrees C. So we're always going to use Celsius in this class. So for science, your experiments, we use Celsius. The weatherman uses what unit typically? Fahrenheit. So like right now, my watch is saying it's, geez, I can't even read. I gotta take my glasses off. 67 degrees out. So 67 degrees Celsius, we would be boiling in here, you know what I mean? So in here we talk about Celsius. So I always think of room temperature as 25 degrees Celsius. So just be familiar with that. And then water boils and condenses at 100. So when you're making your noodles at home, you get the water boiling, it hits 100, that's when you see the steam coming off it. So let's look at this equation here that says autoionization. So ionization means, something neutral is going into it's going into species with charges. So water H2O undergoes autoionization. So that means just by itself with no external stimulus, it's forming a proton and hydroxide. So notice the proton, it has the plus charge, hydroxide has the minus charge. We learned about how you calculate that based on the group, the number of lone pairs, the number of shared electrons. The important thing to note overall is water is neutral. It has zero charge. On the product side, you have a plus and a minus. Those, when added together, also give you zero. So you're not forming an excess of positive or negative charge. Nature, physics does not allow that. You have to balance your charges. The other thing that we'll learn about, let me put in the lone pairs here. So we know water, oxygen is going to have 2 lone pairs. For this oxygen to be negative, it has to have 3 lone pairs. The arrow there means we're going to say equilibrium. It goes back and forth. What I want to make clear, though, is these arrows do not mean 50-50. So that's a tricky thing about equilibrium because it has the word like equal in it. So we want to be clear in our minds that when we talk about equilibrium, it's just the resting state of the system. It does not necessarily mean 50% starting material, 50% product. So at equilibrium under this reaction, you would find that the product side would be very small. So what about the nature of these sigma bonds? What happens to those to become these 2 ions? So we'll talk about arrow pushing, and that's the movement of electrons. So we're going to be sort of scientific accountants where we're keeping track of electrons in lone pairs, in bonds, double bonds. Where are they going to break bonds and to form bonds? That's called the mechanistic pathway of a reaction. So from general chemistry, we learned about equilibrium expressions that have this capital K. And so we're taking the concentrations of the product species, so proton times hydroxide, and then dividing that by the concentration of water. So the products over the reactants. Pure liquid water has this concentration of 55 M. Any questions? So what does M mean? So that stands for molarity, and the units were what? Moles per liter. So that's D. And, to be honest, there's a lot of ways to define concentration. Moles per liter, conceptually for me, is the easiest to understand, but if you remember from Gen Chem, there's other ways. Equivalents per liter, kilograms per liter, moles per kilogram. So anytime you see this square bracket, so like some species A, the square bracket is what means molarity. That's what we're going to use for this class. So the new thing on this slide is basically, see this term here? Since that term is a constant, basically what we're going to do is multiply it by both sides, and then we just fold it into the K value, and then we define it as KW. So the W just means we're removing that concentration of pure water. And what you get with is then proton times hydroxide, and that's equal to 1 times 10 to the negative 14. And so really what should pop out in your mind at this point is this number. Do you remember the scale for the pH scale? So what does it run from? 0 to 14. So now this is where we're going to expand on that, because pH is really defined as what that P means is positive and then H means hydronium. So when you're dealing with water and aqueous systems, pH is defined from 0 to 14. But as I said, a lot of the functional groups we're dealing with are CH bonds. They're not OH bonds. So we have to use another scale called pKa. And then on that scale, it's different. It's much bigger because it has to encapsulate all the functional groups we've learned. So in your recollection, if those concentrations of proton and hydroxide are equal, what word would you describe the system as being at? So B, neutral. So you don't have an excess of either. You remember what pH that would be? 7. So if the proton concentration is greater than hydroxide, what would it be then? So A, acidic. And then relative to 7, is it going to be less than or greater than? So less than. So 0 to 6.99, repeating, that's the acidic region of the pH scale. So I don't think I have the follow-up question, but basically, when you're greater than 7, it's basic. So we can capture that in the table here. So let me just maybe add so less than 7, 7, greater than 7. As we'll see, moving forward, there's a limitation about this because, as this is defined, it's talking about either just proton in relation to just hydroxide. But again, we've learned other functional groups that are different acids. So there's different theories of acidity. In general, this is what you learn from general chemistry. You're talking about doing acid-base titrations. What's the concentration of proton or what's the concentration of hydroxide? So you need to understand, that foundational stuff to really understand how we're going to elevate the definitions of acidity. So the three theories, the first one that you learn, primarily is the Arrhenius. And that deals with the acid as increasing proton concentration and a base as increasing hydroxide concentration. The scope of that definition is pretty narrow. It was broadened by the Bronsted-Lowry definition, where now you're talking about an acid donates a proton and a base accepts a proton. So that broadens it quite a bit because now it can include CH bonds. And then the definition or the theory that describes everything as the Lewis acid-base theory, where you're not limited to proton or hydrogen, hydroxide, or that. You're talking about electrons and their movement. An acid is defined in the Lewis sense as an electron pair acceptor, and a base is an electron pair donor. So that's the broadest definition, and we'll use that for a lot of our reactions because we're really talking about the movement of electrons at this point. So I'm going to scribble a bunch of stuff on this slide, and then the subsequent slides are just individual questions that we can, at that point, go through pretty quick. So we have hydrochloric acid. So within that term is acid. So we're reacting that with water, so water has to be the base. I'm going to write these electron pairs in. So water has 2, chlorine has 3. And what I want to show now is how we get to the product side. So when hydrochloric acid and water react, you form hydronium ion and chloride ion. So let's put the lone pairs in. There's 1 on oxygen and then 4 on the chlorine. So you can see already that water is gaining a hydrogen. It's gaining a plus charge. The hydrochloric acid is losing a proton, and the chlorine is gaining an electron pair. So you see that by comparing two sides, but actually how does it happen? And the way we show electron movement is through curved arrows. So this is going to be a different type of arrow than this reaction arrow. And the learning tool is basically, it shows the trajectory of how the electrons move. And a sports ball analogy that I like to use, it's kind of like football. So the quarterback gets the football, that's the pair of electrons. The quarterback is in charge, and then he's throwing it, he, she is throwing it through a trajectory. That's the curved arrow, that's the path. The receiver is catching it. So you have to draw these in a certain way based on how the terms are defined. So we know that a lone pair on oxygen has to abstract from that HCl. So we start at the lone pair, and at the end, we're going to draw that arrowhead like that. So I know it seems subtle, but I drew like two lines off the arrowhead. That indicates both of those electrons are moving. When we get into module 4, we'll see situations where only one electron moves. So this is 2 electron movement, looks like that. 1 electron movement is called a fish hook. So you notice it only has sort of one line coming off the arrowhead. So the base water is abstracting that proton. Then what happens? Chlorine needs to get a lone pair, and so the flow of the arrows is now from the sigma bond, and it's going to point to the chlorine. And we can rationalize that because we know, based on electronegativity, chlorine's delta minus, and so therefore the hydrogen has to be delta plus. So arrows will flow in that direction. Start, stop, start, stop. What you do not want to do is something like this, where 2 arrows point at the same place. They always have to flow like this. if we look at those three definitions, the arrows that I just drew are validated by all of those. So the acid, in the Bronsted sense, it's donating its H. The water is accepting the H. In the Lewis sense, see this electron pair? In the Lewis sense, the hydrogen, this is where it's a little bit confusing. So this acid is accepting that lone pair. Additionally, the counter ion, the chloride, it's accepting that lone pair from the sigma bond. The base, it's donating that lone pair. So that lone pair is being donated. The acid is accepting it. So keep in mind we're dealing with sort of a mineral acid at this point, HCl. When we get into the CH stuff, conceptually it's the same, but what's accepting and donating might be different. So I said for an acid-base reaction, you have the acid base and then you have the conjugate acid base. So on the product side, what is the conjugate acid? Hydronium. And so therefore the chloride is the conjugate base. And then you just link up the pairs. So water and hydronium are the conjugate acid-base pair. Hydrochloric acid, chloride ion are the other conjugate acid-base pair. But you should be able to look at hydronium and say, okay, now that's an acid because it can donate one proton. Chloride is a base because it can now accept a proton. Or in the Lewis sense, chloride can donate a lone pair. Hydronium can accept a lone pair. So you need to be pretty fluid in how you classify these things according to each theory. So as I said, we'll go through these questions kind of fast. Which species is the base? So that was water. So the action of a base is to abstract a proton. Or again, put another way, donate a lone pair. The conjugate base was chloride. So we can say, if we wrote the reaction the other way, I put these lone pairs in, the arrow would start from chloride, abstract a hydrogen, and go back the other way. The conjugate acid was hydronium. So in any proton transfer, that's a skill you need to have. What's the acid? What's the base? What's the conjugate acid? What's the conjugate base? So again, the how is, for organic chemistry, we refer to that as the mechanism. In football, that would be the actual play on the field. How are the electrons advancing? How's the quarterback throwing it to the receiver? And then to preface this entire discussion, acid-base reactions are really just a small subset of what you're going to learn in this class. So when we get beyond just learning proton transfers and we start learning other organic reactions, we use different terms. We use the term nucleophile and electrophile. That's the broadest sense of classifying any reactant. And that ties in really strongly with the Lewis definition of things because we're talking about electron movement. So again, the double-headed arrow shows the movement of the electrons. And that's the how. It's the mechanism that shows how are these things formed. So when we do start learning reactions, you have your starting materials and your products. And then to understand how that happens, you have to push these arrows. That's the pathway of getting there. So to summarize that, HCl does obey all three definitions of being an acid. So it will increase the proton concentration in water. It's donating a proton to the water, and it's accepting a lone pair of electrons from the water. And then, in terms of matching, a common thing from Gen Chem was doing this sort of connection between the acid-base pairs on each side. Any questions? So that was an example with HCl. Let's generalize it a little bit, and we'll call the acid HA. So we've seen the Lewis dot structure of water here. Water is what's known as a leveling solvent. So that's a pretty special property of it. And what it means is when you take a strong acid, which I'm going to define as HA, and again, A minus is the conjugate base of that acid. You dissolve that in water, you're always going to form hydronium ion as the conjugate acid. And then you get that anion A minus as the conjugate base. So a concept you want to be clear on is when we talk about strength, in general chemistry, you're probably familiar with tying strength of an acid to its concentration. But more realistically, the strength is tied to the ionization. So that H plus A minus, to what extent is that acid ionizing? Not its specific concentration. Because you can have a very strong acid at a low concentration, but it's still completely ionizing. So if you're a chem major, you'll learn more about the nitty-gritty of that in analytical chemistry, and then you'll actually apply higher level math to it in physical chemistry. So that's the general situation there, HA. And so now, because we're dealing with a more broad description of things, we can define the acidity constant Ka. Remember, we already did this for water, now we're doing it for HA. You have the product of the concentrations of hydronium times the conjugate base on the numerator, and then HA in the denominator. So you have that quotient. So that's Ka, and it's going to help us determine the strength of an acid. When we're dealing with these equations, that Ka, and we're dealing with concentrations, we all know, Avogadro's number and concentrations, you can end up with like really large numbers or very small numbers. So what we'll do on these next two questions is just a thought experiment. So we have we're considering the concentration hydronium versus HA. And so in the Ka equation, if hydronium is very large relative to HA, overall, what is the size of the Ka number that would result? So D, a very large number. So for example, if you just put, if hydronium is 1,000 and HA is 1, you get 1,000. So you get a large number. So if hydronium is less than HA, so small, large, overall, what will Ka be? So 1 divided by 1,000, you're going to get a small number. So those are kind of the extremes. So when we talk about large and small, it's at the point where you're using this scientific notation like 10 to the 15 or 10 to the minus 20. So you get to those numbers and it can be hard to think about because the spectrum of numbers between them is so large. So to summarize that, when we're dealing with concentration of hydronium versus the acid, in the first column here, if the concentration of hydronium is greater than the acid, that means the Ka number is large. Chemically, what that's telling you is that the equilibrium is favoring the products, in that the acid is ionizing, so it's a strong acid. If hydronium is less than HA, you get a Ka number that's small. And that's favoring the reactants, meaning that this plus that do not really go to the products that are drawn. So you favor the reactant side, and that's telling you that the acid is then weak. It's not ionizing to a great extent. So that's sort of two bins that help us further define strong versus weak. But as I said, when you do those calculations and you're dealing with these concentrations, you get these numbers that are kind of unwieldy to conceptually, think about and apply to solving a problem. So essentially what's been done is you're basically applying the logarithmic function to each side. So in chemistry, that log function is designated as P. So now we define pKa as the negative log of Ka. And the benefit of doing that, essentially for your very large numbers and very small numbers, it now confines them to a scale that runs from -10 to 50. And overall, there's 60 pKa units. So one thing to note between that scale from negative 10 to 50, when you're from 0 to 14, pKa equals pH. So the column that was added, notice the flip here. When you have a large Ka number and you apply the negative log to it, you end up with a very small pKa value. So there's a flip. So small pKa means a strong acid. When you had the weak acid, which was a small Ka, now the pKa is a large number because of that mathematical operation. And next, what we'll do is look at these strongly ionizing acids, and then see where we really can make a cut in that scale from negative 10 to 50, define what's strong, what's weak, and then we're going to dig down into the weak acids. So remember that water is a leveling solvent. So when you take water plus a strong acid, you're always getting hydronium. And really, the point you want to remember is pretty easy to remember. When you're at 0, so negative 10 to 0, those are your strong acids. From 0 to 50, those are the weak acids, and they encompass all the organic functional groups that we've learned. So the table here really is arranged according to pKa. So that third column, notice I have this number. I just told you it was negative 10. This compound has a pK of negative 14. So the boundaries are not hard boundaries. I mean, you can get things that are even more acidic, but those are other classes, like inorganic chemistry. We won't talk too much about that stuff in here. But you do have, some of these anomalous cases. So when we look at this, going down, negative 14, negative 10, those are strong. As you approach 0, the strength is decreasing. But overall, they're still strong acids. So again, it's all relative. So what you see here is the acid name. So the first one is called trifluoromethane sulfonic acid. We'll talk about this when there's the chemical formula. After you remove the acidic OH, this is the conjugate base. And then the name is trifluoromethane sulfonate. And then, just running down the list, you've seen perchloric acid in Gen Chem, hydroiodic, sulfuric, hydrobromic, hydrochloric. There's hydronium right here. Nitric, hydrofluoric. So we consider all those as strong acids. Any questions? So again, to put this into perspective, there was water, there was sulfuric acid, and then we have this really strong one, trifluoromethane sulfonic acid. The common thing, again, is this OH group, the H that's being donated as the acid. Why is trifluoromethane sulfonic the strongest one? So here's the mechanism of the proton transfer. The water's acting as the base. You see its arrow abstracting that hydrogen. We're now breaking this OH bond, so the electrons are going on to that oxygen. So we form hydronium because it's a leveling solvent. And then this is the conjugate base. So we're going to use the, remember I said, let me highlight in yellow. We want to talk about the stuff highlighted in yellow. What's unique about that that's making it so much more acidic than water or sulfuric acid? So we form this oxygen with the negative charge. So we'll introduce a new concept, and then we'll talk about how this other stuff in the molecule is influencing the acidity. So again, the important thing here is what can we explain about the structural features that leads us to the conclusion about the pKa difference between water, sulfuric acid, and trifluoromethane sulfonic acid. So again, factors affecting acidity. There are two main things. So we use electronegativity quite a bit. And now two other things we can use based on that are resonance and induction. So as shown here with these arrows, we said that oxygen has a negative charge. That negative charge, as we want highlighter, as shown in these arrows highlighted in green, that negative charge can be delocalized through resonance onto all of those other oxygens. And so here, this arrow highlighted in blue, that double-headed horizontal arrow, this is called a resonance arrow. Resonance means the movement of electrons. So you're moving that negative charge around, and what does that end up doing? It's stabilizing the conjugate base, because each oxygen really is bearing a little bit of that charge. It's spreading out the misery, if you want to think of it that way. So think about when we saw that autoionization of water. If you think about that oxygen with the negative charge, it's stuck there. It can't do anything. There's only one oxygen. But in the conjugate base here, that negative charge can go from this oxygen to that one to that one. So it's spread it out, and through that it's stabilizing it. That stabilization makes it happy. And so that can be used as a reason for describing the acidity. Question?
Can there be resonance if there's only two atoms involved, or is it?
So that's a good question. To give you the best answer for that, even though it's not completely relevant to what we're talking about now, if we consider an aldehyde, that's what a normal aldehyde looks like. You can have resonance with two atoms where the pi bond electrons move up onto oxygen. So you can have cases where it's only two atoms involved. But the important thing to remember about resonance is you are not moving the connectivity at all. You have the connectivity of the atom stays the same. You're just moving electrons around. So in resonance, to highlight that, when we talk about electron density, that can mean a lone pair of electrons, so like a negative charge moving around. A single electron, that's neutral. And as we'll learn in Module 4, those are called radicals. So in the scientific sense, a radical is a single electron. We're not talking about the political sense of some revolutionary radical. And again, the arrows are different when we use the curved arrow formalism. Or you can have kind of no electrons, and those are a different species. Those are called carbocations. So the more resonance hybrids that you can draw, the more stable it is. But keep in mind that resonance hybrids can contribute different amounts to the stability. The other thing I want to point out, you see how the way I have to draw this due to the physical limitation of like teaching and learning. I have 1, 2, 3 structures. In your mind, do not think of this as 3 different structures existing in time and space. The best way to think about it is it's one structure with, say, negative 1/3 charge on each oxygen. It's just showing you where the electron density is. It's not 3 distinct or discrete things. So that's resonance. The other factor is induction. And I did introduce this in Module 2 when we talked about, we had that 4-carbon chain with the heteroatom. How does the heteroatom influence the chemical shift as you move away from it? And that's the tug of war argument, induction. What we're focusing on now is the fluorines. Fluorine's a heteroatom. They're not drawn in there, but each fluorine has 3 lone pairs. That's why I put that delta minus. So essentially what happens is because that delta minus charge, so that highlighted in yellow there, and I drew these bonds in blue. The fluorine is greedy in the sense that it's the most electronegative element. There's this negative charge down the chain, and it's like, I want some of that. So through the bonds, it's pulling that negative charge, that sigma bond network that's highlighted in, drawn in blue, highlighted in green. So it's that tug of war. It's helping to stabilize that negative charge because it's so electronegative. So if we look at this collection of 4 different acids, and let me highlight again the OH, 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 OH. What we're looking at is this part of the molecule that has CF3 and a pK of -14. If you just have H's, that pKa is -1.2. So if you think about substituting an H for F, then 2 F's, then 3 F's, the acidity is increasing. So that demonstrates the effect of how the heteroatom fluorine increases acidity through induction. So to calibrate you on what I just said about the NMR argument. Say you had that compound. You have a fluorine in there, but it's way down the chain. So it can't help as much because it's going through a lot of bonds now. And really the way to think about that is, see this CH3 group? This whole thing now sort of resembles CH3 because that's so far away. So the pK of this is probably similar to that negative 1.2. So let's talk about a group and some other factors that affect acidity. So these are the hydrohalic acids. The commonality is now you have H bonded to a halogen. You see the formulas HF, HCl, HBr, HI. And then you see this bond length. So that A with the little circle on it, that's called the angstrom. And that's defined as 10 to the negative 10 meters. What do you notice about the pKa values here? So HF through HI. HI is the most acidic. So that can be a general misconception. People think of HF as being the most acidic of that group because we've always said, well, fluorine's the most electronegative. So within that group, the bond strength bond difference between F, HF through HI, fluorine, really, HF should be the most acidic. But the difference is when you're going down that group, the size of the halogen increases. So HF you can think of like as a golf ball, HCl maybe an orange, HBr, I don't know, maybe a basketball, and then iodine, HI is a big beach ball. The consequence of that is the H is constant, it's staying the same size. But when you get down to the HI, you have like a beach ball bonded to your little proton. So they don't really have a strong bond to begin with, meaning that they're almost ionized to begin with due to the size difference. And that size difference helps explain the acidity. And then as you go down that group as well, fluorine is really compact. In chemistry, there's another theory of acids and bases called hard-soft. Fluorine is hard, iodine is soft. It's big and squishy, it's polarizable. So it accepts that a lone pair of electrons a lot easier than F will. So again, HF, it starts with the strongest sigma bond between hydrogen and then those group 7 elements. HI has the weakest sigma bond, so you can think of it as almost being ionized to a greater extent. And due to the size, you have increasingly poor orbital overlap, which means the bond is weak. And then another term we use is polarizability. So that means the diffuseness of the electron density. So C, N, O, F, Cl, Br, I. So in red, I'll say that's the electronegativity trend. And then in blue, the trend runs opposite for polarizability. So just like with, the periodic table is based on trends. That's why it uses the word periodic. So organic chemistry really is based on trends. And so if you put the work in to understand the trends, as you learn new reactions and concepts, you don't have to memorize, 500 different things. You can just categorize it as a trend. Questions? So a couple more slides before we wrap up. So again, now it says strong versus weak. So strong acids are ionized in water to form hydronium due to the leveling effect. We use those acids as reagents in organic reactions. But now here is the main issue. However, the majority of functional groups that you learned are weak acids. And so to understand relative to one another, what is the strength of those weak acids, we have to use the pKa scale. And so in this region, -15 or -10 to 0, those were strong. But now we have this huge region, 0 to 50, that encompass all the weak acids. So that's spread over 50 pKa units. The other thing to keep in mind, since we're on a log scale, when we talk about like a pKa difference, if you have a pKa difference of two functional groups, where it's say pKa of 20 versus pKa of 17, the difference is 3. But in reality, since it's a log scale, that's 10 to the 3, and it's 1,000-fold difference in acidity. So remember, the pKa is just a compression that allows us to deal with smaller, more manageable numbers. So in our last 2 minutes here, these were all the functional groups that you learned from modules 1 and 2. The second column is giving you an example of each. So for a carboxylic acid, we have ethanoic acid, which is acetic acid we saw. Acetic acid has a pKa of 4.75. You don't have to kill yourself trying to memorize things out to digits. I go by units of 5. 0, 5, 10, 15, 20. And then associate amongst that what functional group is close to that. The conjugate base is then shown. So notice that the conjugate base of acetic acid has a negative charge. And then the name. Notice the second line here. Protonated ammonia is called ammonium. See how it's starting off with a plus charge? Its pKa is 9.2. Just call it 10. Now notice its conjugate base is ammonia. It's neutral. So you have to keep in mind what you're starting with to figure out what the charge on the conjugate base is going to be. So read through these functional groups. What you're trying to do is make an association between the functional group and the pKa. We'll pick back up with this on Monday. But if you think back to that gifratoxin, which is the next couple slides, after you've deprotonated the OH, what's the next functional group to get deprotonated? And you're looking at these numbers to figure that out. So that's what we'll start with on Monday.
Thank you.